Hi, for this lesson we're working on pages 4 and 5 of our Theme 13 booklets. This is a photograph taken on a field trip of a cliff at Broadhaven in Pembrokeshire. The reason I want to show you this is that these rocks have been deformed. There's been a stress applied to these rocks and we see the results of this. We see the strain of this rock because it's deformed. The layers that you see in this rock were originally flat and horizontal. If we pick out how one of these layers has actually been deformed and follow one layer through the cliff, we can see just how much deformation that there's been. Now, what I'd like you to do is, bearing in mind what we've learned already about the different types of stress and the different types of deformation that can occur as a result of that stress, I'd like you to label up this photograph, annotate the photo to show how this rock has actually been deformed. Okay, use as much of the language that we've been covering the last couple of lessons as we can. If you're not sure the exact words, don't worry about it. Describe what you see. So, press pause now and have a go at that. Okay then. Hopefully you've now got some annotations on that photograph, on that image. I want us to dig a little deeper into this though. I want us to think about why these rocks are responding this way. And to do that, we're going to use a superb example of a composite material. We're going to use a Mars bar, because a Mars bar has three different components. It has the chocolate, it has the nougat, and it has the caramel. If we put a stress on these materials, they will deform. We will see strain. And we can see different types and different amounts of strain in our stressed Mars bar. You can try this at home as well if you like. Let me show you my Mars bar experiment. A Mars bar is an example of a composite material. There are three different materials that go together to make up a Mars bar. We've got chocolate, we've got nougat, and we've got caramel. What I want to do with this experiment is to put some stress on a Mars bar and see how these different materials actually deform. Let's start with this one. Okay, so we've got Mars bar. Let me apply a stress. You can see already that the chocolate has deformed, has failed. I keep applying the stress. We can see that the caramel is deforming. And we can also see how the nougat beneath it has deformed as well. Think about how much stress it's taken to deform each of these. Think about the type of strain that each of these materials has demonstrated. Okay, so that's our first example. Let me open another Mars bar. And now let's put this under some stress. You can see this one has deformed in a very different way. What's different, do you think? What's changed from this Mars bar to this one? The chocolate, you notice, has deformed in quite a similar way. Although we can see perhaps the effect of tension at the top and compression at the bottom. The caramel, though, has really behaved quite differently. How is that deformed compared to the first one? What do you think is different between these two Mars bars? This Mars bar has been at room temperature. The second Mars bar has been in the freezer. So what we have is exactly the same materials that are at different temperatures. Notice, though, the same change in temperature between the room temperature Mars bar and the frozen Mars bar has had a different effect on each of those materials. Now, perhaps we need to think about the significance of this in terms of geology. We know within the Earth, we see materials that are at different temperatures. The deeper they are in the Earth, the higher the temperature. Does that perhaps go some way to explain why rocks that we think of as cold, hard, and brittle may actually fold, flow, and deform in a way that, as if they were much, much softer? Okay. What I want us to do now is think about how we could show some of these results on a stress and strain graph. Now, this is a graph that tries to show the link between these two factors. Stress is on the vertical axis, strain is on the horizontal axis. Notice, though, there are no numbers on this. This is just to try and show an idea. Now, we've got several parts of this graph. You can see the first part here, going from the beginning up to point A, is a straight line. That represents elastic deformation. From point A to point B, we see a change in the angle of the slope. So for very little extra stress, we're getting a lot of strain. This part of the graph represents plastic or ductile deformation. The line then stops at point B, where no more stress will lead to strain. That's where the material is broken. Let me try and show you how this works. So for the new guy in our room temperature Mars bar, we can draw a line that looks a little bit like this. A small amount of stress leading to very little elastic strain. The new guy then starts to bend, for a small amount before it breaks. What I'd like you to do now is on the graph on page 5, is I'd like you to draw in stress strain curves for these 4 materials. For the room temperature chocolate, for the room temperature caramel, and then the frozen chocolate and the frozen caramel. Think about how much stress it took to deform those materials. Think about the strain that they demonstrated in that video. Once you've done that, then explain your decisions. Why have you drawn curves like that? So press pause now and have a go at that.